folks, I'm going to start with study guide problem 15 and then work through the summary and then make a separate video for the quest. So 15 says this: what is the height of a building in meters if it takes a rock 4.1 seconds to drop from the roof? So this is just like the lab we did in class. And you're going to use the equation distance equals 1/2 acceleration times time squared. Okay, so it wants the answer in meters, it says. So you need to use the acceleration due to gravity as 9.8 meters per second squared down. You can call down negative, you can call down positive, as long as you write something in the answer to tell that you know that height is a vector quantity because acceleration is. So you need to give some indication of direction, whether it's putting a positive or negative sign in the answer or writing a word like the building is so many meters high or up or down or any sort of word that tells direction. So we'll just plug in. We want to know the height of the building, the distance the rock falls. So we have 1/2. Acceleration is 9.8 meters per second squared. I'm going to keep it positive. Well, let's make it negative. It's kind of traditional to think of that as down. And then it says the rock took 4.1 seconds. And in the equation, time is squared. So what you'll type in your calculator is 0.5. And yes, please let your parents see the video if they are questioning. You may use a calculator for this. It's very useful to use a calculator at this point. So you're going to type in your calculator 0.5 for the 1/2, or you could do 1 divided by 2, times 9.8 times 4.1 times 4.1, because 4.1 is squared. So don't forget that part. And when you type that into your calculator, you should get 82.4 or something like that. Maybe if there's a 100th place, I rounded. If you don't round, that's fine. I think maybe if you leave it or if you round, it's fine. Round to the tenths is fine. I'll teach you how to really round numbers in chemistry. But then you have to think about units. Distance should be in meters, so you can kind of think of it that way. But it's important to use your units when you show your work so you can check to see if you did the problem right. So meters is in the numerator, and then second squared is in the numerator. And then here, this second squared is in the denominator. So the second squared in this numerator and the second squared in the denominator cancel each other, leaving only meters, which is what we would expect. And then remember, we've got a negative sign here. So that negative sign would show direction, that I'm thinking about direction. If you had made acceleration positive, this positive sign would show that you're thinking that this is a vector quantity, and that would be acceptable. Or if you just wrote something like the building is 82.4 meters up, down, high, any words will do the job and let me know that you're thinking about vector quantities. You have to have some kind of directional information. But since you can decide what up and down are, you can decide what kind of words you use. Number 16, a balloonist drops a rock from his balloon. It takes 7 seconds for the rock to fall to the ground. What is the balloonist's altitude in feet? Well, same equation. This equation you can only use also if the object you're dropping starts at a velocity of 0. So you can't use this, you have to use a slightly different equation if you throw the rock or whatever you're dropping downward. So this is only if you drop something. We use this for the lab because we were measuring the ball falling, and so when it reached the highest point, it came to a velocity of 0, and then we started the stopwatch and timed it on the way down. But if somebody had thrown the ball from the ceiling, we would not be able to use just this. We'd have to account for the initial velocity. So it says in feet, so we're going to use acceleration as 32 feet per second squared. And we can make it negative again because it's going down. That's kind of traditional. And then it said it took 7 seconds to hit the ground. So time 7 seconds squared. So in your calculator, you'll type 0.5 times 32 times 7 times 7. And should come up with something like 784. Of course, these second squareds cancel these second squareds, so feet. Then we have to say that displacement is a vector. So I put a negative here, I'll put a negative there. That's one of the ways you can show the vector. And then number 17 says, a scientist decides to measure acceleration by measuring the distance a moving object travels in a set time interval. The scientist noticed that every 30-second interval, the object travels less distance than it did in the previous interval. Is the direction of acceleration the same as velocity or opposite to velocity? So if acceleration and velocity are pointing the same direction, that object is speeding up. In this case, the object seems to be slowing down, so acceleration and velocity are pointing in opposite directions. We talked about that a little bit in class. So now we'll look at the summary. We never get to go over that, but with the extra math, that's definitely a struggle for many students, this extra math, so let's make sure we cover that too. So the summary starts here. Every science relies on the science of physics. As a result, we call it the most fundamental of all the sciences. The science of mechanics is the branch of physics that deals with analyzing and understanding objects in motion, the forces that are applied to those objects, and the energy that exists in them. When studying motion, one must define a reference point, which is a point against which position is measured. If an object's position relative to this point is changing, the object is in motion relative to that point. Because motion depends on a reference point, all motion is relative. The units for speed and velocity are composed of a distance unit divided by a time unit. That can be any distance divided by any time. In base metric units, speed is given as meters per second, while speed simply tells you how quickly an object is moving. And remember, speed considers the actual path. That's not even a straight line, right? If I go from point A to point B, if I'm worried about speed, I have to get the distance of the actual path. So where am I? Speed simply tells you how quickly an object is moving. Velocity tells you how quickly an object is moving and the direction in which it moves. So if I want to know the object's velocity, I just go straight line from point A to point B, and that's the distance that I divide by the time. And thus speed is a scalar quantity, no directional information given, while velocity is a vector quantity. Speed can be calculated with the equation speed equals distance divided by time, or you can do distance equals rate or velocity or speed. This is speed or velocity times time. Little dot means times. That still throws my son off. Speed is distance divided by time if you rearrange that. Rate or speed, velocity is distance divided by time. And I hope you guys are starting to get comfortable rearranging equations like that. If this is kind of foreign material, please make an appointment and see me, and we'll just have a little math lesson to make sure that that is good. Let's see. When objects travel the same direction, their relative speed is the difference between their individual speeds. When they travel in the opposite direction, their relative speed is the sum of their individual speeds, which is why a head-on car accident is so much worse than a rear ending, because here is the difference between their speeds. Subtracting, good. Here, adding the speeds, very bad. This is number 5 now. The time rate change of an object's velocity is its acceleration. So time rate change of velocity is sort of confusing way to put it, I think. But what it really just means is acceleration is the change in velocity divided by the change in time. Acceleration is change in velocity divided by change in time. The units for this quantity are composed of a distance unit divided by a time unit squared. In base metric units, this would be Velocity is meters per second, and time is seconds, right? So meters per second divided by second really equals meters per second squared, acceleration units. It is a vector quantity because acceleration has to contain directional information. So don't forget to put directions on the test. It can be calculated with the equation, well, right there it is. Or you can find if the object's in free fall and it starts at a velocity of 0, you can use this one that we've been using to find acceleration. So, number 6, an object with an unchanging speed can still have an acceleration provided its direction is changing. Like if you're going a constant speed around a turn, your direction is continuously changing as you turn in a circle or a curve. So even though your speed is constant, your direction is changing, so your velocity is changing. If direction is changing, velocity is changing. In physics, the term acceleration can also mean an object is slowing down. We don't say deceleration. It just means that your velocity vector and your acceleration vector are pointed opposite directions. Acceleration is simply a change in velocity, whether speeding up or slowing down. Decreasing velocity is still a change in velocity. If an object is speeding up, its acceleration is in the direction of its velocity. If it's slowing down, its acceleration is in the opposite direction of its velocity. And if you guys learn that now, physics will be so much easier. That one is something that still confuses students, even in 11th and 12th grade. But just master that, and that would be awesome. Number 7, when an object falls solely under the influence of gravity, we say it's in free fall. In such a situation, the acceleration is equal to 9.8 meters per second squared down. And if you don't say the down part, you don't get full credit. And in metric units, 32 feet per second squared down. In English units. 9.8 is metric, 32 is English. The acceleration is independent of the characteristics of the object. Therefore, in true free fall, a feather and a bowling ball fall with the same acceleration. So remember we talked about that, how air resistance affects like the piece of paper more than the book. But if we had a vacuum, or if the paper is allowing the book to push the air out of the way for it, we can see that it's the case that the paper and the book fall at the same rate, the feather and the bowling ball fall at the same rate. And if you go to Air and Space, make sure you play with the vacuum tube, because that's really fun. And you can probably find a YouTube video, like if you search, feather, penny, vacuum tube, you'd probably get a video of that, so you can see that really is the case, that the feather and the penny fall at the same rate. Number 8, when an object is in free fall, the distance it drops can be calculated with the equation. It was right there before, d equals 1/2 at squared. Number 9, although we generally treat objects falling near the surface of the earth as if they were in free fall, air impedes the fall of objects, so things don't truly free fall unless there is no air. Although things that are very aerodynamically shaped come pretty close. However, for most objects, the effect of air resistance can be ignored. The golf ball, hopefully, we used was pretty aerodynamic. Thus, when most objects fall near the surface of the earth, we can assume they are in free fall, unless they're paper or a penny. Not a penny, a feather. When doing an experiment in which error is a known problem, you can reduce the effect of error by making several measurements and averaging the results. And we saw that with the stopwatch. Some of us were fast on the stopwatch, some of us were slow, hopefully some of us were right on. But when we average everyone's data, it is more likely that we will get close to the truth, right? An accurate answer. So number 11, what is the speed of a boat that travels 20 miles in 45 minutes? Please answer in miles per hour. Okay, so 20 miles is the distance. And I really like to lay out all the data before I start the problem. If you struggle with math, I think it's really important. So the time is 45 minutes. And we're supposed to answer in miles per hour. Well, if you think about a clock, right, 45 minutes, say 15, 30, 45, 60. So 3/4 of the way around is 45 minutes. So we don't really have to do a big conversion here because we can figure that's 3/4 of an hour. So then we can just use distance equals rate times time. We're solving for speed, which is rate here. So that will be distance divided by time. So we'll do rate equals 20 miles per 3/4 of an hour. You can plug into your calculator here, 20 divided by 0.75, for example, and you should get 26.7 or so. And that's miles per hour. So rate, it's asking for speed in this situation. Speed's not a vector quantity, so you don't have to worry about giving me directional information. If it said velocity, then you would have to worry about it. Number 12, label each quantity as vector or scalar. Identify it as speed, distance, velocity, acceleration, or none. All right, so A says 10 meters per second squared north. That gives a magnitude, it gives a unit, that is an acceleration unit, meters per second squared, and it gives a direction, so that's acceleration. It's a vector quantity. B, 1.2 meters per second, no directional information. Meters per second would be speed or velocity. Since it's not giving direction, it's going to be speed. It's scalar. C, 3.4 feet per hour and slowing. Slowing doesn't tell me what direction it's actually going. So 3.4 feet per hour is going to be a speed, it's scalar. D, 2.3 miles per minute west. That gives a magnitude, a unit, which is speed or velocity, and a direction. That means it's velocity, it's a vector. Number 13, a sports car goes from velocity of 0 to a velocity of 15 meters per second east in 2.1 seconds. All right, so I like to start writing down initial velocity is 0, final velocity was 15 meters per second east. It took 2.1 seconds, time is 2.1 seconds. And it wants to know what's the car's acceleration. Well, if I have this information, I just use the definition of acceleration, which is change in velocity divided by change in time. So that's final velocity minus initial velocity divided by change in time. So we've got 15 meters per second minus 0 meters per second divided by 2.1 seconds. So 15 divided by 2.1 basically gives us 7.1. And then think about units. So you have meters per second divided by seconds. So that's going to be meters per second squared, which is good news because that's a good acceleration unit. And if velocity was going east, and this guy was speeding up, then it's going to go east. So the acceleration has to have a magnitude, a unit, and a direction. 7.1 meters per second squared east. Number 14 says, what is the height of a building in meters if it takes the rock 3.8 seconds to drop from the roof? So, I hope my camera hasn't run out. So here we'll use distance as 1/2 acceleration times time squared. We are trying to find the height of the building, so distance. Let's see, we're given no necessary direction about, oh, it does ask for meters. So we'll use acceleration as 9.8, I'll go negative, meters per second squared. So it's kind of indicating down. And the time was 3.8 seconds. Now we've got to square the time. Type in your calculator, 0.5 times 9.8 times 3.8 times 3.8. Or you can use the square button, but just make sure you don't forget to square the time. So then we end up on that one with 70.8. This is negative. That'll show that I'm thinking about direction. We have meters per second squared times second squared. So that cancels out the second squared, leaves us with meters. So if I look at this answer, I tell about direction, I have magnitude, and I have units, so that covers the vector issue, or you can just use the word like the building was 70.8 meters high, or down or up or anything. I guess the rock's falling down, so height of the building. Number 15, a car and a truck are traveling north on the highway. The truck has a speed of 42 miles per hour. The car has a speed of 37 miles per hour. If the truck is ahead of the car, what is the relative velocity? All right, so truck is going 42 miles per hour north. The car is going 37 miles per hour north. So they're going the same direction. So the truck is, of course, pulling ahead of the car. So you just do 42 miles per hour minus 37 miles per hour. And you find the difference is 5 miles per hour north. So remember to give directional information there. They're pulling apart at 5 miles per hour north. Number 16, if an object travels for 10 minutes with a constant velocity of 11 miles per hour north, what is acceleration? So don't be fooled. Anytime you have constant velocity, there is no acceleration, because velocity means the speed isn't changing and the direction isn't changing. If speed's not changing and direction's not changing, whether that object is at rest or moving in a straight line, then you have an acceleration of 0. No change in velocity means 0 acceleration. Number 17, a car is traveling 55 miles per hour south. It brakes suddenly, and it takes 3.5 seconds for the car to come to a full stop. All right, so initial velocity is 55 miles per hour south. Now we do know also final velocity, even though it doesn't say it's 0, because it comes to a stop. So don't be fooled and think you don't have enough information. It takes 3.5 seconds for the car to come to a stop. What is acceleration in miles per hour squared? So it tells you, luckily, that 1 hour is 3,600 seconds. So you want to get miles per hour squared, which means we have to convert 3.5 seconds to hours. So we use that conversion vector it just gave us. 1 hour is 3,600 seconds. We want to get hours. We want to cancel out seconds here. So 3.5 divided by 3,600 seems like kind of a crazy number. And in fact, you can use your calculator, obviously, and I get 0.000972 hours. So really, time equals 0.000972 hours. Wow, that's a fun number. Okay, so then we just plug that in, even though we have big, tiny decimals here. Don't worry. Plug in for acceleration. Then you have acceleration is final velocity minus initial velocity divided by time. So final velocity was 0. Initial velocity was 55 miles divided by hours. And our time was 0.30972 hours. So now we have miles divided by hour, so that's miles per hour squared. This 55 ends up being negative because of the equation. So we're going to end up with an acceleration that's negative. We had a velocity that was positive. That just shows that velocity and acceleration are pointed in different directions, which makes sense because the car is slowing down. That's what we expect when the car is slowing down. So acceleration is going to be negative 56,000, and I think it's like 571 miles per hour squared. And the velocity was south, we can see acceleration is negative. So instead of that negative sign, you could have said 56,571 miles per hour north, right? The opposite direction of the velocity. But the negative sign takes care of the vector direction, if that suits you also. So just a confusing conversion there, but no problem. It gives you the conversion factor even. So 56,571 miles per hour squared. And then you have to show direction either with a negative or by saying north, because velocity was south. Last one. How far in feet did a dropped rock fall that took 2.3 seconds to reach the ground? So our old buddy, 1/2 AT squared. So we're looking for how far. We want in feet, so acceleration will be 32 feet per second squared. Time was 2.3 seconds, that quantity squared as well. So multiply 0.5 times 32 times 2.3 times 2.3, and you find distance to be 84.64 feet. You can say down, up. We could have made this negative, so we ended up showing direction. So I'll come back with another video for the quest. Do your work before you watch the video.